Hello, everybody. Hope you're doing well. Just a small disclaimer. My presentation is not going to be as artistic as the last presentation. It's going to be solid concrete. Okay, so I'm going to be talking about mechanochemical activation for the production of SCMs. I'm Sofiane Amroun, by the way. Third-year PhD student at the University of Miami, and this is the topic of my PhD work. Okay. So the presentation is going to be split into three parts. The first part is the longest, and then the two other ones are very short. The first part is mechanochemical activation on basaltic fines, okay? I'm going to define all of these terms, guys. Just small background, as we all know, there's a shortage of typical SCMs such as fly ash, slag, silica fume compared to the cement demand in the world. The tendency nowadays, of course, is clays, calcined clays. We all heard of them. For my research, I'm using basaltic fines that falls under the fillers, and we have a lot of it. Earth's crust is full of basaltic fines. It's made mostly of basaltic rocks, sorry. So basaltic fines can be used as SCMs, and there's in literature people that use the basaltic fines as a supplementary cementitious material. The good thing about basaltic fines is that they are available, relatively low cost, and they have adequate chemistry to be used as SCMs since they are aluminosilicates in the most part. Basaltic fines are in general very crystalline, so they are inert materials. So before using them as a cement replacement material, it's better to activate them. I'm not saying we cannot use them as they are. We can, but they're going to be inert materials, so the replacement level, the limit for the replacement level is quite low. So for activation, the typical way is to use furnaces and high temperatures, just like calcining clays, for example, to turn the material from crystalline to amorphous, so from inert to reactive. For my research, I use something called mechanochemical activation. So basically what it means, we don't use any furnace. We take the material, we put it in a jar, we use grinding beads, we put the powder inside, and we grind at very high energy. So the mechanical energy that's transferred to the material actually can alter the structure of the material and turn it from crystalline to amorphous, so from inert to reactive. So what I did here, I took basaltic fines with the XRF composition that you guys see. It's mostly silica. It has some alumina and iron. I put it in the planetary ball mill. So the planetary ball mill is not like regular mill that we know. The planetary ball mill works like this. So we have the jar, we put the material inside with the beads, and then it turns just like a planet. So it turns around itself and around the center. The grinding speed we used is 400 rotation per minute, and throughout the whole presentation, the grinding speed is 400 rotation per minute, RPM. I varied the grinding time, so 15 minutes, 30 minutes, 60 minutes, and the ball to powder ratio. This is a super important parameter. What it means is the ratio is the weight of the balls, so the grinding media divided by the powder ratio, and we're going to see actually the importance of this parameter. So I varied it from 5.2 to 20.6. So 5.2, 7.7, 10.3, 20.6. Just as a reference, a BPR of 20.6 is equivalent to 30 grams of material inside the jars, and 5.2 is 120 grams, okay? So after grinding the material, so mechanochemically activate them, I run different tests, actually before and after, SCM, XRD, particle size distribution, BT surface area, and the modified R3 test, which is a reactivity test that I'm going to be talking about shortly. So for the results, the picture in the left, so this is the raw basaltic fines, and we can see that it's very coarse, very rough surface. And these two images are from the same sample activated at 60 minutes at 20.6 BPR. And we can see the formation of three different types of particles. We can see the very small ones that are right here. We can see agglomerates, so these very small particles agglomerate together, and this is a very known effect of mechanochemical activation. And we can see aggregates like we see here. So we see a particle that's roughly just like a raw BF particle that's surrounded with very small particles that we call aggregates. So these are agglomerates and these are aggregates. Particle size distribution, it's very hard to understand what's going on in the particle size distribution, but the black curve represents the raw basaltic fines, okay? And after activation, we see the three different peaks actually, 1, 2, and 3. And this actually correlates with what we've seen in the SCM. For me, I think that these are the fine particles, these are the agglomerates, and these are the aggregates. So the coarse particles surrounded with very small ones. And the difference between the two figures here is just the BPR. This is 5.2 BPR, and this is 20.6 BPR. So we already can see the effect of the BPR. For the BT surface area, yes. So this is the raw material. This is the material activated at 15 minutes, 30 minutes, 60 minutes at different BPRs. We see a huge increase in surface area at the beginning, and then it goes down. This is, like if we think about it, this is unexpected, right? Like if we grind the material, we expect the surface area to increase, so the material becoming finer. But because of the agglomeration that we've seen from the SCM images, there's actually a decrease in surface area, and this is also a known effect in the mechanochemical activation process. But nevertheless, the surface area of all the materials is higher than the raw material. Okay, so now about the XRD. This is the raw material, very crystalline. We measured the degree of amorphization, or the degree of crystallinity. The degree of amorphization is just 100% minus the degree of crystallinity. This is 5.2 BPR, and this is 20.6 BPR. And by the way, like we've done this on all the BPRs that I showed, that you just don't want to saturate the slide, so I'm just putting 2 BPRs. With grinding time, so the lower we go in the figures, the higher the grinding time. So with grinding time, we see an increase in the degree of amorphization, so an increase in degree of amorphization, so a decrease in degree of crystallinity. And with the higher BPR that we use, so again, higher BPR means like we're putting a very small amount of powder inside the jars. We see degree of amorphization after 60 minutes of 77%. And one note on the XRD is that it's phase specific. So there are some phases that get amorphized very easily, and other ones that take a while to amorphize, just like the quartz. And this is because of the hardness. The quartz has very high hardness, so it's very hard to amorphize. Still on the XRD, so this figure shows the grinding time and the DOA. DOA is degree of amorphization. So with the increase in grinding time, as we've seen from the XRD figures, there's an increase in the degree of amorphization. And with the increase in BPR, so we put less powder inside the jars, we have a way higher degree of amorphization. Yes, so the modified R3 test, this is the reactivity test I told you about, guys. So this is developed by Jason Weiss and Dr. Panoy Sarayaneni. I don't know if you know about the ASTM C1897. This is a modified version of that. So basically what we do, we take an SCM or any material that we want to replace cement with partially. We add CH, an excess of CH. So the SCM, the CH, calcium hydroxide, and alkaline solution. We mix them together, we put them in calorimeter, and we measure the heat release from the reaction. So obviously, the higher the heat release, that means more reaction is happening and more reactive the SCM is. So I've done this on all the materials that I've processed. The black curve here is the basaltic fines raw before any activation, and we see that it's inert. There's no heat that's released basically because the material is very crystalline. With the increase in grinding time, we see an increase in heat release. This is 5.2 BPR again, and this is 20.6. And yeah, the higher the BPR, the higher the increase in heat release, so the higher the reactivity. This curve here shows the heat release at 72 hours, which is the last point here, for all the BPRs and all the grinding times tested. For BPRs that are 5.2, 7.7, and 10.3, we can see that there is like quite a linear increase with grinding time. But when we go to the 20.6, there is like a leveling off of the heat release over time. And this is like quite expected. We're not expecting the degree of amorphization or the heat release to increase forever, right? It's going to level off at some point. And this is what we see here. Yeah. So we have the heat release data and we have the degree of amorphization. And in literature, it's known that the degree of amorphization has a huge effect on the heat release. And we see in this curve a very good correlation between the two. The R squared is actually 0.94. And this is in the case of mechanochemically activated materials. So what this means is that if you remember, the surface area curve increases and then decreases, but nevertheless, the degree of amorphization is correlating with the heat release. And we try to correlate the degree of amorphization and the heat release with the surface area, no correlation at all. So we concluded that the degree of amorphization, or the amorphous content of our SCM, is what dictates the reactivity of the SCM, not the surface area. So actually another conclusion, potential conclusion from this, is that the agglomerates that you guys see that make the surface area decrease actually dissolve in solution and doesn't have much effect on the reactivity. So this is the first part. The second part. So, okay, the mechanochemical activation is good. It's increasing the reactivity. We said, okay, let's pick a parameter. We're not going to vary the BPR. We're not going to vary the gradient time, and apply this on a lot of materials, not only basaltic fines. So we took 11 more SCMs. We're still testing more, but for this presentation, I'm showing 12 SCMs, so 11 plus the one I tested. So we have mine tailings, glass slag, ground granulated blast furnace slag, two types of fly ash, clays, ground glass, olivine, and 3 different basaltic fines. These are the XRF data. So we activated them at 20.6 BPR, 30 minutes. Okay, we didn't vary these parameters. And we plotted the curve. That's one of the best curves in the presentation, guys. This is the initial this is the initial heat release before activation. So the raw material before any treatments, the heat release, so from the reactivity test, and the x-axis. And the y-axis is the increase in heat release after activation, after mechanochemical activation. So what this curve shows us is that if you have a material that's initially inert, it has way more potential to become more reactive after mechanochemical activation. If you have a material that's initially quite reactive, if you try to mechanochemically activate it, you won't have as much benefit as if your material is inert. One other thing that's seen from this curve is that if your material is inert, which are these materials that you see here, all of them can be considered inert, there's a huge variability in the increase in reactivity. And that's actually something we're trying to look at, like what causes this material to have this increase and this one to have this increase. We're looking at different stuff, especially the composition, the phases in the materials, the hardness, etc. So this was the second part. The third part is mechanical properties of mechanochemically activated materials. Okay, we've seen the reactivity, but we want to see compressive strength, right? We're going to see some compressive strength data, guys. So what we've done, we took 2 SCMs, the basaltic fines, low kaolinite clays. We activated them at 60 minutes, 10.3 BPR. We used 10.3 BPR, not 20.6 as the part 2, because when you use 10.3 BPR, you have a yield that's higher. So at the end, you're going to get more material, so more material to play with. If we use 20.6, we would have only like 30 grams at the end. This is 60 grams. We got these 2 materials after activation. This is just the notation, BF60, so 60 minutes, 10.3 BPR. And we made cement paste with it and water. 30% replacement in both cases. On the cement paste, we're on isothermal calorimetry. So we took cement paste sample and we put it inside the calorimeter to measure the heat release. And on the mortar, we did the slump flow test, compressive strength, and electrical bulk resistivity measurements. On the cement paste, the isothermal calorimetry, the black curve is the PLC, so the control. In all cases, the heat release decreased. Why? Because we're replacing 30% and our materials are not like metakaolin or silica fume. They're not that reactive to have a higher heat release at 7 days. And this is 23 degrees Celsius, by the way, so ambient temperature. But these 2 curves that you see down here are the raw materials, and the ones that you see here is replacement with mechanochemically activated materials. So even in cement paste, we see an increase in heat release. That means further extent of the pozzolanic reaction. The slump flow test, this is the control. PLC control is the highest. This is an ongoing research, by the way. So I'm pretty sure that the main reason for this is the particle size distribution of the PLC that's a bit coarser compared to the BF. BF is basaltic fines. Before and after activation, there's not much change in the slump flow. But for the LC, there is a huge increase. And from the PSD data that I'm not showing here, this one is coarser than this one. So even our material got finer, but the slump increased. And this is mostly because of the particles that we are forming. If you remember, guys, they were like more spherical compared to the raw material, and that's the effect we see here. And for the basaltic fines, there's not much change. We can't talk about it. We're still trying to understand what's going on here, but I most likely feel that it's because of the porosity, because the basaltic fines before activation were not porous at all, but after activation they were porous. Yeah, there's a lot of discussion on this, and we can talk more about it later. Compressive strength and bulk resistivity. So the main outcome of this is that the raw materials, which are the BF and LC, showed less compressive strength compared to the activated ones, especially after 7 days. So this is 7 days, and this is 28 days, compared to the raw materials that are here, because of the increase in reactivity again. The bulk resistivity, the main outcome is that the activated materials showed a way higher bulk resistivity, which can be translated to high durability indexes. Just giving you a second to look at the figures before I skip. Okay, conclusions. Basaltic fines can be used as a source of SCM because we've seen the reactivity. Actually, sometimes we got to high reactivities compared to fly ash, and we all know that fly ash is used extensively in the field. Mechanochemical activation caused an increase in surface area, as we've seen it, a complex particle size distribution. We saw the agglomeration, the aggregation, the particles becoming more spherical. Longer grinding, higher BPR increased the reactivity. Amorphization is phase specific. And we were able to show that mechanochemical activation works for a lot of materials, mostly the inert ones. And yeah, we've seen improvement in heat release, motor flow, strength, compressive strength, and bulk resistivity compared to the raw materials. So yeah, that's pretty much it. And thank you very much, guys.